Good afternoon, everybody. Thank you for having me. Before I start, I want to give you maybe a quick poll. How many people here actually look at logs on daily basis? Wow. All right, that's the right room then. So today we're going to talk a little bit about finding relevant events, logs, and alerts. So within all of these logs and events and alerts that you have, which of them are actually relevant? And a little bit about maybe breaches. Have anybody here done incident response with logs and forensics after a breach? Okay. So after a breach, trying to piece together the story is one part, but also before the breach is another part. But imagine you're after a breach. Imagine a breach has taken your organization and you've lost some data and you've lost customer, respect. You've lost a little bit of the stock price in the stock market. But what you're looking at is how did that happen? And when you're thinking about it, you're like, let me go piece together the story and figure out where did it go wrong? What did I miss, right? Usually, as we were talking, we have a lot of alerts. So looking through that and trying to figure out where to put the blame is a little difficult, especially with attacks usually being less than 9% of your traces. So most of the traces that you're looking at are not part of any attack. Most of the traces by default are part of probably lone incidents, not really a full attack chain, or something that's essentially benign. And on average, finding the right stuff before you even know that there's a breach would take you up to a year. So it's almost like an impossible task. And in theory, it sounds very easy, but it doesn't seem very easy from a practitioner's point of view, even though we have a lot of tools. So what makes it so bloated and ineffective? Well, the SANS surveys, and you probably fill a lot of these SANS surveys yourself, seem to mention correlation, seem to mention this idea of writing some sort of logic that would somehow put all of the relevant things together. And this is in 2025. We are years beyond rules, we are years beyond playbooks, we are years beyond machine learning, we are well into generative AI, and we are still complaining about correlation, something that's very, very basic. Way before I was born, people were essentially mastering basics of engine rules and essentially machine learning for clusters. So what is so challenging about actually correlating? Why is this so hard? Well, to understand this, imagine you have a lot of assets, a lot of accounts, a lot of entities, and entities are essentially always putting buzzes on you. They're always buzzing with some sort of a log, something happened, look here, right? All these traces. Some of these little traces together form a good story, and finding those is either through a retrospective hunt, right? You know exactly what kind of story you're looking for, have it from some sort of a threat intelligence piece, and you're retrospectively looking for it. Does anybody do threat intelligence retrospective hunting? Okay. And most people probably just have a correlation rule. You guys have correlation rules? A little bit. And the majority of people probably don't do neither. No correlation rules and no essentially retrospective hunting backstory. So most people are working in silos. They're looking at every event on its own, and they're using their own minds, their own hypothesis to put it together. Anybody here actually thinks that they're really good at putting together things with their mind? If I give you a way to look through your logs, you're able to piece together stories based on hypotheses. Okay, so it's very, very challenging. And a lot of people would essentially just refer back to playbooks. Anybody here uses playbooks? Okay, playbooks are a little bit more, usable. So depending on whatever playbook you use, whatever tool you use, from Jenkins to N8N, a SOAR platform, whatever it is, right? You essentially write a flow of logic. You say, if you see this, and then you see this, then do this. Usually there's some sort of enrichment, usually some sort of put them together in a little case or something like that. The problem is usually the attack looks like this. So this is an attack that took over Singapore Health. Anybody here familiar with Singapore Health? That was a while back. Okay, so Singapore Health, as you can see here, this is the attack story. I put it together in a little chart that goes vertically with time. You can see here all the way to the left. See, it's August 2017 is when the attack started. And going left to right, you see the MITRE attack tactics. So you can kind of think about it as this is an entire attack campaign. And as I go vertically, I'm seeing time. As I go horizontally, I'm seeing attack advancement or attack progression or attack lifecycle, right? And the idea is every little color over there is a different machine type or a different entity type, right? Because I have entities, I have time, and I have sequentiality. So these are my 3 dimensions. 2 dimensions are in the little chart, other dimension is the color. So on the entity side, you see like they started with machine 0, and then they kept on going through machine 0 all the way up until they had command and control on that machine. So that was completely on that endpoint. And then they did some sort of lateral movement, and they went into a completely new machine. And they went into that new machine because that machine was probably closer to some sort of like an identity access that they needed. And after they were done with that machine, again, all the way through. So this is not like every machine essentially saw a little bit of an attack chain, but then when you zoom out, it took multiple machines, it took multiple identities, and it took multiple networks, as we'll see. So see, they went into another server 1 month later. So they fully compromised up to command and control 2 machines. And then 1 month later, you restart at another machine, at another server machine. So a lot of assets are being essentially used in this kind of attack chain. And then they take a while. They take like a few months of a break. And they come back after August 2017. They come back closer to December 2017, right? And they use one of the older machines that they had access to. And they continue the attack, and they go into this new, essentially, new asset here, the workstations, an entire group of workstations, entire domain of workstations, an entire network of workstations was used in January 2012. And they just continue to compromise different assets on different parts of the network. And if you go a little bit further into the next 6 months, see they keep on doing the same thing. Long story short, they compromise over essentially 20 assets from identities, devices, network components. And that takes them up to August 2018. We're talking an entire year of an attack chain that essentially embodies a few little attack chains that essentially affected different scopes. Like the little scope of the first machine, the little scope of the second machine, and so on and so forth. They all look like they're closed investigations or closed cases. But when you zoom out, this case keeps on getting bigger. Long story short, if an attack looks like this, how would you put it together in terms of your playbooks, or in terms of your rules, or in terms of essentially your manual investigation or manual threat hunt? It's almost possible. To make it even worse, not only did they use multiple machines and multiple networks and multiple entities, went over a year and essentially fully compromised multiple assets, they also did this with multiple attack vectors. So if you were threat actor profiling them, or threat actor attributing them to whatever happened, would have a lot more difficulty because they're not using one tool anymore, or essentially tools that are associated usually with one threat actor, but they're using a variety of tools. We're not sure why they did that in this case. It might have been because they wanted to throw the security team off, might have been because they just kept on trying new things. But regardless, we've seen at least 5 different attack kits, from exploit kits to phishing kits to rats and so on and so forth. And there was a few worms as well. I don't think I included them there. But essentially what you would like to do is you would like to see this entire attack attack kill chain. Depends on what terminology you use. There's like attack flow, attack story, attack kill chain, attack timeline. Marketing people usually come up with a lot of names, but essentially the idea is you want to see it all together. And it's pretty hard to see it all together before it happens, because it's pretty hard to see it all together after it happens. So essentially, if you were trying to figure out what is related to an event, and the previous speaker was talking about essentially log management as well and log analysis as well. And if you have a lot of logs, you ideally at least want to bundle them. Ideally, at least aggregate them. You don't want to have 500 syslogs telling you the same thing. They're like 99% redundant. Like, you don't want 500 telemetry events from the same network session. You don't want 1,000, I guess, sysmons from same session on one workstation. Ideally, you want to bundle. Ideally, you want to aggregate. Even better, and bonus points, you can dedupe within these groups. Because if you can deduplicate within these consolidated events, you essentially get easier data management. You probably save a lot of money as well in terms of compute, storage, licensing for a SIM or whatever. Kind of like get a lot of data, like 10 terabytes, and essentially shrink them into like 1 terabyte just by deduplicating. That's how redundant the information is. And on top of that, you ideally want to also contextualize it with what stage. Like just giving me a syslog is no good. What am I going to do with a syslog? I want to know what this syslog maps to in terms of an attack tactic, in terms of an attack technique, right? I want to understand the context. I could probably understand it manually. If I read it, probably understand it. If I put an AI on it that's very well trained, but I want to do it at scale. I want to understand every single log, every single event, every single alert, exactly where it fits in my attack techniques and attack tactics, and I want to group them so that I have essentially the aggregations and the bundling, the consolidation of these events, and on top of that, also want to correlate. So I have a lot of things that I want to do today. So the idea is take a lot of siloed signals. We know a lot of people siloed events today, siloed signals, siloed traces, siloed logs, events, and alerts that are not connected to each other at all. Ideally, I want to take them through this process of contextualization and correlation and spit out consolidated events for everything so that I can see the entire bundle, I can see the entire consolidation for every single event. But also on top of that, I want to see the fraction of events that seem to make together a well-formed attack chain or attack story or attack narrative. All right, so how would I do that? How could I possibly do all of that? Well, you can think about it as how can I correlate logs, events, and alerts? Ideally, I want to figure out which of my little events form groups, like which of them actually form things that are part of, let's say, one session, right? What else other than one session? Maybe one community ID, essentially based on source IP, source port. Maybe it's part of the same application session instead of networks. Maybe it's part of the same endpoint login session, right? Like you could have a lot of different formalities of what a session means, right? Like you do a lot of different groupings. But the idea is you want some sort of a grouping that tells you what's going on at different levels. So how do we get this grouping? Well, in machine learning, you can essentially get this grouping without writing any rules at scale for free with technology from the 60s or from the 70s. So this is the same technology that when I was a little kid and I opened my first MySpace account, told me that this profile is related to this profile. This is the same technology that I go today on Instagram, LinkedIn, whatever it is, and it tells me this profile is related to this profile. This reel is related to this reel when I'm like scrolling like a maniac, right? So essentially, very basic technology, very scalable, very explainable, but for some reason not adopted in cybersecurity because it would take a while to take a look at these things. But essentially, I think it's a pretty good time to look at it. It's been in Splunk machine learning toolkit for a while. It's been used in multiple notebooks. We have a lot of good adoption today. Machine learning notebooks in data pipelines. So timing works out. It's easy. We'll go through it today. We will consider it in this kind of correlation aspect. And let's see how it plays out. So clustering seems to do essentially the basics of what I need. It scales better than correlation rules. Don't have to write the correlation rules. At the same time, it scales, it's fast and it's cheap to do it. Cheaper and faster to do it than rules. But at the same time, complements my rules. My rules are looking for specific patterns. I already know that this is how it looks like. Clustering essentially does it at scale for every 10 terabytes, 100 bytes. It's going to work out. And it's pretty easy to essentially get a clustering model to work out for you. ChatGPT can generate the code essentially. I also have this completely open. So let's start this clustering idea. Sure. Let's build a clustering model for my logs. How does it work out? Well, you run into the problem of, I need to figure out what's my input data size, what's my context data size, what's my timeline, what's my time span, what features am I going to group things on? Am I going to group them based on the same user? Or am I going to group them based on the same business unit? Or am I going to group them based on the same device? Or am I going to group them based on the same process, same hash, same attack technique? What am I grouping on? The features that I'm going to group on are very important. Well, I have to figure that out. And I also have to figure out how to do basic data normalization and feature mapping for the machine learning to work out. And that's why people don't really like to do machine learning, because you have to do a lot of, I guess, consulting or a lot of structured project, I guess, engagements. However, it seems to get a little more complicated than this. It doesn't stop at this. So you also have feature enrichment. Remember, we wanted to understand the causality or sequentiality for every single log. That meant that essentially every single event needed to be put into an attack technique or an event category or some sort of a framework, either a CVE or something, right? The mapping or the enrichment also is going to take a bit. And if you use the attack techniques from vendors, through our research, we found that essentially almost all of the vendors put attack techniques for marketing purposes. So the attack techniques and the rule sets are not exactly very accurate because they are trying to maximize the coverage. At the same time, most of these are repurposed from open source repos, open source rules that are developed by very different people writing rules with very different tactics that you cannot really count on. You're operationalizing something. So when you're operationalizing attack techniques and the MITRE attack framework, you really find it hard to essentially do that enrichment properly. So the enrichment, in this case, is going to be an entire new model of own that we're going to also talk about. But not only that, you also have to look at what makes things similar. Because if you have the exact same identical port, that's not usually similar enough for the groupings to be big and meaningful. Groupings of different events and logs and alerts can also happen based on similar processes, similar registry keys, similar ports. What's an example of a similar port? Like if I'm looking for something in port, I don't know, like 443, a similar port is an alternative port, 8443, right? To a regular machine learning that doesn't know this, it thinks that 444 is closer to 443 than 8443, right? Because the numbers are closer. So you also need to teach the model essentially this kind of encoding. Not only that, you'll also have to pick a model and configuration. So this is essentially your blueprint if you want to get a consultant to work on this entire project. And it would be one of your best projects, by the way. Like this would be a fantastic project, a one-time investment, and you'll probably get a lot of data consolidation out of it. You'll save a lot of money on the big data that you have, that you're processing. You'll save millions on the licensing alone in multiple stems. But essentially, we'll make it even easier. You don't have to do this in consulting. It gets a lot easier, and you don't have to despair. Because clustering seems to check out all of the little boxes. We can use it to expose coordinated attacks, because these little clusters or these little groupings or consolidated events, I can then correlate them a lot easier. They will have the tactics. I can write my rules on top of them. Also, I can essentially get the contextual awareness, because when I look at one event that's consolidated, I kind of see, similar root cause. I kind of see the attack path. I kind of see what's going on in that little bundle. So I get a lot of context. And not only that, I'll also be able to augment it with current technologies, because it's not replacing any of the platforms. It's happening upstream. So everything downstream from SIM, SOAR, threat hunting platform, threat intelligence platform, whatever it is, they're all downstream after your data is already consolidated, right? Like it wouldn't even touch your cloud before it's already consolidated if you put this in the right place in your architecture. So let's make it work. For instance, for input data and context size, there are machine learning tools today that allow you to not choose the machine learning or context size. Everything. They are called temporal clustering. Temporal clustering allows you to essentially no more have to deal with old classical clustering. Temporal clustering essentially allows you to see all of the data. So for instance, something that happened today can be clustered with something that happened yesterday. Although the time span or the batch size maybe is like an hour or two, the model will remember and will figure out something that's essentially happened previously in its memory, and it will still group on that. So solves you the problem of figuring out the input data context size. Also, for figuring out the features to be considered, you can also use something called knowledge graphs or knowledge-based engineering. Knowledge-based engineering means that all of your data will be considered, and you'll just plug it into essentially a framework for the data representation. What are some good frameworks? Well, Veris is a good one. OCSF is a good one. Stix is a good one. You can essentially look at every single feature you have, leave absolutely nothing behind. And then in terms of feature mapping, well, you know how it is. Today we have semantic models, we have natural language processing. It's not pretty hard to do mapping. No one has to sit down and write exactly the correct mapping for this source type, exactly the correct mapping for this data feed. That is old news. Today you can do it with an AI like ChatGPT. You can do it with a natural language processing model, which you can ask ChatGPT to write you. And we also have our own source that you can use. So now that the technologies are making all of these problems disappear, let's take a look at the other set of problems. Well, for instance, the feature enrichment. The feature enrichment one is pretty hard to do without, a specialized model that can do MITRE ATT&CK relevancy mapping or classification for every single event. Good news, you have AI and you have NLP models and you have big rule sets of essentially exactly what to map an event or rule or log to, and you can double check it and you can ensure that this is trained for essentially machine learning classifier model that can look at any single event or any single log or any single some sort of like an alert, and it would generate this lookup table that goes from this signature to this technique. So pretty easy to do today with NLP and AI advancements. Data encodings as well, pretty easy to do today if you have the right knowledge engineering and plug it in. You can already get these kind of things with ChatGPT as well if you want to build it in-house. Or again, use our open. Clustering models and configurations. Today, you have the compute, you have the power, framework, you have the products that allow you to run essentially 500 models next to each other, and they will be cheaper than what your team is budgeting today for an AI compute resource in-house. Like now your team probably has a GPU in your office, and 5 years ago you didn't have that, so today you can actually run all the models and configs at the same time. It doesn't matter. They're cheap compared to AI. So now that we essentially can put these little attack techniques tags on all of our data, we benefit from essentially the enrichment of, yes, now that I have a technique and tactic, for those that don't know it, obviously, you get a lot of information or background information about every single event. So imagine if every single event, you have a description of what's going on, you have detection advisories, mitigation advisories, you can also map it to CVE, you can map it to compliance platforms. Thanks to the MITRE project called Mapping Explorer, you can essentially map any MITRE technique to like a million other frameworks. And on top of that, you can do attack actor attribution or threat actor attribution. You can attribute that these techniques probably came from this tool. These techniques probably came from this actor. These techniques probably came from essentially this kind of organization, and so on and so forth. But the beauty of it is now that you have techniques, you're able to form attack chains. Without techniques, you cannot put attack chains together other than with very, very specific correlation rules that look for very, very specific event codes. When you have this abstraction layer of MITRE ATT&CK technique, you're fully operationalizing the framework of MITRE ATT&CK. When you operationalize this framework, you're able to actually see that this technique comes from this tactic. This other event also affected the same entities or relevant entities within kind of the same time, maybe 5 minutes, maybe 10 minutes, maybe 10 hours. It depends on the context. Maybe 10 days, depends on the context. But it's kind of sequential because this is tactic 1 and this is tactic 4. And they kind of happen in this essentially attack chain or attack narrative or attack story. And there's a project, anybody knows about MITRE ATT&CK Flow? There's a project that was newly released a while back. It's called MITRE ATT&CK Flow. They essentially use it to show the well-known breaches, how they kind of flow together. So let's actually build it. So let's build what we talked about. So we talked about getting all of the relevant MITRE ATT&CK techniques for every single event log or alert. Fantastic. That's a classification model. Second, we're going to group things. We talked about clustering. We said that today clustering can solve all of the challenges that used to happen before. That's why we didn't have clustering before. Today, there is no excuse not to have it. And then the third part is the correlating of these groupings or these consolidated clusters into revealing MITRE ATT&CK chains or MITRE ATT&CK flows, or whatever you want to call it, that essentially looks like an attack. So let's start with a classification model. How do we do that? Well, very basic classification model. You can even use an LLM. I would really suggest use an NLP model. Essentially, you just remove the first L and it becomes a language model. But if you want to use large language model, you can. You can open ChatGPT or a local llama or a quantized essentially language model, and you would get this language model and you would give it, as we did, unlabeled corpus of all of the events, and then you would give it a small labeled corpus for the fine tuning. That this is an event, this is a technique. I'm going to give you a bunch of events from now on, and you give me the exact technique that I should map it to, and you make up this little lookup table, and you use it for enriching everything that you're ingesting. Essentially, it's going to look something like this. So you would put any sentence in the world. The model will give you techniques with confidence. I obviously hid the confidence from this little view, but you'll get confidence thresholds that you can also set up. So now you can make up this lookup table pretty easily, and you can enrich everything you have with techniques and write better rules on top. However, we don't stop there. That we want to consolidate, we want to group things. I want to go to my stock director or CTO or whatever and tell them, you know what, I saved you, I don't know, $10 million on whatever SIM that we're using today because I consolidated everything without any filtering or stripping of the data, completely lossless consolidation, grouping and deduping. Let's do the grouping. How do we do the grouping? We essentially cluster events that are related. How do we do that? We put them, as mentioned, in a structured data format, if you remember, BERES, OCSF, Unified Cyber Ontology, whatever it is, the data structure that you will use. The one that we're using is similar to BERES and STIX, OCSF, and UCO, kind of mushed together into like a new little fork of them. But you can also use whatever data structure that you would like for these kind of groupings. And then we essentially take these little events, and every event in that grouping gets an embedding. What's an embedding? Essentially a number, like a coordinate system that tells you this event is here, the XYZ coordinates for this event is there, and this other event is closer to this than this. So pretty easy embedding of these kind of events that we now put into that data structure to form these connections of. And now we feed this into a clustering model, and boom, we have clusters, get the clusters, and we essentially deduplicate in them. And we put out the data that's deduplicated, again, 10 terabytes into 1 terabyte or more, because you essentially get at least 90% consolidation or reduction when you form groups that are on average 10 things, because usually the deduplication removes pretty much all of the data. All of the data is redundant in most of these kind of logs, and so you end up with essentially 90% reduction at least. And then after that, we go into correlation. What is correlation? Essentially, what I want to do is I find these groups or these clusters that can form a story that is sequential or that is causal. How do I know that they're sequential or causal? Any idea? Any thoughts? Pretty easy. You have the tactics, you have the techniques, remember? So from the previous enrichment, everything has a technique. If I have the technique, I have the tactic. And if I know that this group of events is tactic 1, events is tactic 2, and the group of events is tactic 1 is affecting the same entity within the same time span of the group of events that are tactic 2, I essentially chain them together. Again, at scale, pretty easy, pretty cheap, and pretty explainable, and nothing wrong with it at all. And it can essentially also support your rules. Your rules would trigger on things that are already correlated. But what we would do is essentially we would put all of the stages in a model called the Markovian model. Again, a model from the 60s. I intentionally chose very old models for this so that it doesn't seem like I'm showing something that's super new or breaking through, other than the little components that we discussed in the clustering. But this, for instance, is a very, very old model. It's called Markovian model, and it's a sequentiality model, a sequencing model. You give it things that are enabled with some sort of an enrichment that tells you about causality or sequentiality, like the miter attack tactics, and it would form them together into sequences that are probabilistically very likely that they happen. So in this case, things that essentially are stage 1 or tactic 1 would be put with things that are tactic 5, even though they're missing things in between, because they're still probabilistically together. So it's not a deterministic rule, it's probabilistic chain. So that's the benefit of machine learning, is you don't actually need to have every single thing. You could have blind spots, you could have 0 days, you could have whatever, but you would still, given enough pieces still form the story, right? And still ideally see the entire attack chain before it's too late. And that would essentially take you into some of these experiments that we ran, taking a big number of alerts into smaller groups of these attack flows that were correlated. And it looks something like this. Again, the same visualization that I shared earlier, but this time on a little UI for the people that are going to use the tool. And what you see here is a graph showing you the entities that are involved on the left. The entities are kind of color coded. And then every little card is essentially like a bunch of events. So you can see the events are like 3 events per card or like 4 events. One of the cards has 10 events or something like that. And every card is essentially just an aggregation. And then all of these things are kind of put together in a flow. You can see these flows at scale, again, very, very cheap for a ridiculous speed and a ridiculous, again, scalability. Like I think we ran 10 terabytes on a very small Docker machine. It ended up coming back in like less than 5 minutes. So none of these are particularly hard to scale or hard to run at big data numbers. Again, same difference. Essentially, you can see it in stages or tactics. It doesn't really matter in terms of what you get in terms of reality. You choose the enrichment that you want, either kill chain stages from cyber kill chain from Lockheed or MITRE attack tactics, but essentially the same idea stands: rich, group, dedupe, correlate. Pretty easy. So you essentially end up with something like this: enrichment, then the grouping, the correlation. And some people might have been using pipelines. Have anybody here used like a pipeline to reduce or filter the events that go into the analysis? Okay. So this would work with your pipeline. So you can see here, for instance, like 100 terabytes are going into my code data pipeline before it hits, let's say, my SIM. And what I'm seeing here is I can write my user-defined filtering in tools like, whatever tools or ETL tools are out there today. But on top of that, I can, after I'm done my filtering, trimming, sampling, transformation, and aggregation that is user-defined, I then pass it to my machine learning. And in this case, I took 100 terabytes. I did user-defined filtering to make it 90 terabytes. I dropped out some things. But then I gave the 90 terabytes to this machine learning, essentially group and dedupe, as well as enrich and correlate. But the group and dedupe alone, or the consolidation alone, took the 90 terabytes into 1 terabyte. So same data. Like the first one had filtering and trimming. The first one actually lost some data. The second one, thanks to machine learning, is completely lost because it's essentially group a lot of things, dedupe all the redundant values, didn't lose anything, right? You can also use it without essentially all of the pipeline if you don't want to. In this case, 100 terabyte and 1 terabyte as well in these tests. And then essentially this is like a little bit of a review of the things or the functionalities that you want to install in your diagrams or in your architecture or in your experiments or in your lab. You want to install some sort of an enrichment for everything. You want to install some sort of a group and dedupe so that you get these consolidated events. And then you also want to install some sort of correlation. And if you use machine learning for all of these, it's essentially fully contextualizing all of the data that you have, which is essentially the holy grail of everything that is going to come after downstream. Like you would really enable your SIM, your rules, your playbooks, your SOAR, your AI, your team, your hunters, whatever it is that's going to come downstream to do a lot more with that data, since it's going to be a lot higher quality. I have some, I guess, data schemas or data structures for different optimizations, but obviously with the open source tool, you can get whatever data schema you want, so it doesn't really matter that much. But essentially, you can lower the level of expertise, because whenever I talk to people, they're like, oh, we never really find security expertise. It's really hard to find. I don't think so. I think we just require very high levels of expertise. They are supposed to know how to do a lot of these things on their own and supposed to contextualize things on their own. And a lot of people are contextualizing today with AI, which is going to hallucinate and going to take them on a very wrong path. Because seniors can tell when the AI is doing really bad. Juniors cannot tell. So if you want to empower juniors, you probably want to empower them with something that is not like going to hallucinate or something. You want to get like a structured data science or machine learning model that's going to do exactly 1 or 2 tasks at a time. And you can tune it and easily make sure that it's doing its job properly. But essentially, needless to say, less expertise and focus would be needed for investigators if you give them the right context. So less mistakes would happen. And things like Sing Health or Singapore Health shouldn't happen in the future with these basic machine learning contextualization that we discussed today. I'm very grateful for the time. I really appreciate the opportunity and looking forward to your questions.